There was a time, how innocent that phrase now sounds, when humanity believed that time itself was a kind of cosmic river flowing uniformly through the universe. It was thought to pass with perfect indifference to the stars, to the planets, to you and to me, whether one stood upon the surface of the earth or floated in the distant silence. Between galaxies, time was assumed to tick in obedient regularity, like a divine metronome. This was the inheritance from the magnificent mind of Isaac Newton. In his vision, time was absolute. It existed independently of events. He wrote of it as something that flows equably without relation to anything external. It was not influenced by matter, nor by motion, nor by gravity. It was the stage upon which the drama of physics unfolded, but it was not itself an actor. And for centuries, this view served humanity well. The motions of the planets could be calculated. The tides could be predicted, the paths of cannonballs obeyed clean and elegant laws. The universe appeared mechanical, precise, and beautifully obedient to mathematics. Time ticked the same in London as in Jupiter's orbit, the same in the heart of a mountain as in the vacuum of the heavens. But there was an itch. The itch began not with gravity, but with light, when we discovered that the speed of light denoted by the symbol c remained constant for all observers, regardless of their motion. Something profound was disturbed. Imagine two observers, one standing on a platform, another riding a swiftly moving train. If both measure the speed of light, both obtain the same value. See, this defied the intuition inherited from Newtonian mechanics. According to classical reasoning, velocities should add, and yet they did not. The only way to preserve this constancy was to sacrifice something more sacred than velocity. We had to surrender absolute time. In special relativity, time was revealed to be elastic. If one moves at velocity v relative to another observer, the time measured by the moving observer, let us call it t prime, is related to the stationary time t by the relation t prime equals t divided by the square root of 1 minus v squared over c squared. In narration, this becomes time experienced by a moving observer equals the stationary time divided by the square root of 1 minus velocity squared divided by the speed of light squared. Already, time had lost its universality. Motion could stretch it, but this was only the beginning. The deeper revolution came when we turned our attention back to gravity. Newton described gravity as a force between masses, proportional 2g times the product of two masses divided by the square of their separation. That is, F equals g times m1 times m2 divided by r squared. This equation worked magnificently, but it treated gravity as an invisible pull acting across empty space. I began to wonder, what if gravity is not a force at all? Consider this thought experiment. Imagine you are inside a closed elevator. If the elevator accelerates upward, you feel pressed against the floor. Now imagine you are standing on Earth. You feel weight pressing you downward. Can you distinguish between these two experiences without looking outside? No, this equivalence between acceleration and gravity became the seed of a deeper insight. If acceleration affects time because motion affects time, then gravity must also affect time, for gravity and acceleration are locally indistinguishable. Imagine now a beam of light crossing the elevator from one wall to the other. If the elevator accelerates upward, the floor moves slightly toward the beam during its transit. To an outside observer, the light appears to curve. Thus, acceleration bends the path of light. If gravity is equivalent to acceleration, then gravity must also bend light. But if gravity bends light, then gravity must influence spacetime itself. Light does not bend because it has mass, it bends because spacetime is curved. The geometry of reality is altered, and if space is curved, can time remain untouched? No. Space and time are not separate kingdoms, they are woven together into a single fabric spacetime. To curve one is to curve the other. Thus, in the presence of mass, time itself slows. This is not metaphor, it is measurable. The stronger the gravitational potential, that is, the deeper once it's in a gravitational well, the slower time flows relative to regions of weaker gravity. Near a massive object, the rate of time is given by a factor involving the square root of 1 minus 2 times g times the mass m divided by r times c squared. In narration, time near a massive body equals time far away, multiplied by the square root of 1 minus 2 times the gravitational constant times the mass divided by the radius times the speed of light squared. as the mass increases, or as one moves closer, that is, as r decreases, the quantity inside the square root shrinks, the flow of time diminishes. Thus gravity does not merely pull on matter, it pulls on time itself. Near the surface of Earth, this effect is tiny but measurable. Atomic clocks placed at higher altitudes tick slightly faster than those at sea level. Satellites orbiting our planet must correct for this discrepancy, or their navigation signals would drift disastrously. But near a black hole, this effect becomes extreme. Time does not simply slow, it nearly halts relative to distant observers. The world before this understanding imagined time as a universal rhythm. The world after recognizes time as local, relational, and dynamic. It is not a rigid ruler by which events are measured. It is clay, molded by mass and motion. Gravity is no longer a force acting within time, it is a sculptor shaping time itself, and once one sees this, one cannot return to the old view. The ticking of a clock is no longer innocent. Every tick is a negotiation with the curvature of the cosmos. When we approach a black hole, we are no longer speaking in poetry. We are speaking in geometry, and geometry, when taken seriously, becomes destiny. To understand gravitational time dilation near such an object, we must consider the solution to my field equations found by Carl Schwarzschild in 1916. Remarkably, he derived it while serving on the Eastern Front during the Great War. In the midst of artillery and mud, he uncovered a description of space-time around a perfectly spherical, non-rotating mass. This solution tells us how spacetime is shaped outside such a body. It reveals that space and time do not merely bend, they intertwine differently depending on how close one stands to the mass. Let us focus not on the full metric, but on what it tells us about time. Imagine two observers, one hovers safely far away from the black hole, so distant that spacetime is nearly flat. The other hovers at a distance are from the center of the black hole. Both carry identical clocks. Both believe quite reasonably that their seconds are ordinary seconds, yet they are not. The relationship between the time measured by the distant observer, call it t far, and the time experienced by the observer near the black hole, call it t near, is governed by a simple but profound expression. Time near equals time far multiplied by the square root of 1 minus 2 times g times m divided by r times c squared. In narration form, the proper time experienced close to the mass equals the time measured far away multiplied by the square root of 1 minus 2 times the gravitational constant times the mass of the black hole divided by the radial distance times the speed of light squared. This square root is the heart of the matter. Let us examine its anatomy. G is the gravitational constant, the quiet proportionality that measures how strongly mass curves spacetime. M is the mass of the black hole, the architect of curvature. R is the distance from the center. And C, the speed of light, is the cosmic speed limit, the conversion factor between space and time. Now observe the structure. Inside the square root, we see 1 minus something. That something grows larger if the mass increases. It also grows larger if the distance decreases. Thus, as one approaches the black hole, the subtraction becomes more severe. If r is very large, if you are far away, then 2 times g times m divided by r times c squared becomes tiny. The square root approaches 1. Time near and time far are almost identical, but as r shrinks, the fraction grows, the quantity inside the square root decreases. Time near becomes smaller relative to time far. The clock close to the black hole ticks more slowly, and then we encounter a special radius. This is the Schwarzschild radius, defined by the condition that 2 times g times m divided by r times c squared equals 1. Solving for r gives r equals 2 times g times m divided by c squared. In narration, the Schwarzschild radius equals 2 times the gravitational constant times the mass divided by the speed of light squared. At this radius, something astonishing happens. The expression inside the square root becomes 1 minus 1, that is, 0. The square root of 0 is 0. Thus, according to the distant observer, time near equals time far multiplied by 0. In other words, from the viewpoint of someone infinitely far away, time at the event horizon stops. Let us be careful. This does not mean that the person falling toward the black hole feels time stopping. Their own clock ticks normally. Their heartbeat proceeds with tragic regularity, but signals sent outward from them become increasingly stretched red-shifted as they climb out of the gravitational well. To the distant observer, the infalling clock appears too slow, too freeze, and too fade. Why does this happen? The Schwarzschild solution tells us that the time component of spacetime is scaled by that square root factor. Gravity reshapes not only distances but durations. The deeper you descend into the gravitational well, the steeper the slope of time itself. One may visualize this as a funnel. The black hole sits at the bottom as you move. Inward, the walls of the funnel become steeper. Climbing outward requires more energy not only for matter but for light itself. A photon emitted near the horizon must struggle upward, losing energy. Its frequency decreases. Since frequency is inversely related to time intervals, the clock that produced that photon appears slowed. Mathematically, this slowing is not arbitrary. It is encoded precisely in that square root. Notice also the symmetry of nature's design. The factor 2 times g times m divided by c squared carries the dimensions of length. It defines a characteristic radius purely from constants of nature and mass. No material property of the black hole enters, only its mass. All else is irrelevant. Thus the logic is complete. The equation does not merely predict that clocks run slower near massive bodies. It tells us exactly how much slower. It predicts that as r approaches the Schwarzschild radius, the flow of time relative to distant observers approaches zero, not gradually, but asymptotically, never quite reaching zero from the outside perspective, yet approaching it without mercy. This is the mathematical heart of gravitational time dilation near black holes. It is not mystical, it is not metaphorical, it is geometry speaking in the language of square roots. And that square root is the quiet gatekeeper between ordinary gravity and the abyss. There is a boundary in the universe that behaves unlike any other. It is not made of stone, nor of fire, nor of any material substance. One may cross it without feeling a wall or striking a surface, and yet, once crossed, return becomes impossible. This boundary is what we call the event horizon. To understand it, we must revisit the special radius we uncovered earlier. The Schwarzschild radius is given by the relation radius equals 2 times the gravitational constant times the mass divided by the speed of light squared. In narration, the critical radius equals 2 times g times m divided by c squared. This is not merely a convenient number. It marks the location where the escape velocity equals the speed of light. In classical reasoning, the escape velocity from a spherical mass is given by the square root of 2 times g times m divided by r. In narration, escape velocity equals the square root of 2 times the gravitational constant times the mass divided by the radius. If we now ask, at what radius does this escape velocity equal the speed of light? We set the square root of 2 times g times m divided by r equal to c squaring. Both sides yields 2 times g times m divided by r equals c squared. Solving for r gives r equals 2 times g times m divided by c squared. Thus, at this radius, not even light can escape, but this classical derivation, charming as it is, does not capture the deeper truth in general relativity. The event horizon is not merely where escape velocity exceeds light speed. It is where the geometry of spacetime tilts so radically inward that all possible future paths point toward the center. Return to the time dilation expression. Time near equals time far multiplied by the square root of 1 minus 2 times g times m divided by r times c squared. As r approaches the Schwarzschild radius, 2 times g times m divided by c squared, the quantity inside the square root approaches zero. Thus, from the perspective of a distant observer, time near becomes vanishingly small. Imagine watching an astronaut fall toward the black hole. As they approach the horizon, the signals from their spacecraft take longer and longer to reach you. Each pulse of light is stretched, its wavelength elongated, its frequency diminished. This is gravitational redshift. The frequency observed far away equals the emitted frequency multiplied by the square root of 1 minus 2 times g times m divided by r times c squared. In narration, the observed frequency equals the emitted frequency times the square root of 1 minus 2 times the gravitational constant times the mass divided by the radius times the speed of light squared. As r approaches the horizon, this square root shrinks towards zero. The observed frequency approaches zero. The light fades into darkness. To you, the distant observer, the astronaut appears too slow, freeze, and dim, never quite crossing the boundary. And yet here lies the subtlety: for the falling astronaut, their own proper time continues. Normally, the equation governing their experienced time contains no singularity at the horizon. They cross it in finite proper time. Their watch ticks, their heart beats, their thoughts proceed uninterrupted until tidal forces perhaps end the story deeper within. How can both descriptions be true? The answer lies in perspective. Coordinates used by distant observers become ill-behaved at the horizon. The apparent freezing is a feature of the coordinate system, not a physical wall in spacetime. When one adopts coordinates that move with the falling observer, the horizon is revealed as an unremarkable region, at least locally. But globally, it is profound. Inside the horizon, the radial coordinate R behaves like time. Just as we cannot move backward in time, an object inside the horizon cannot move toward larger R. All future directed paths lead inward. The singularity is not a place one travels to voluntarily, it is a moment in one's future. Thus, the event horizon is not merely a surface in space, it is a boundary in causality. It separates regions that can communicate with the outside universe from those that cannot. To the distant observer, the horizon is a place where clocks appear to stop. To the infalling observer, it is a one-way membrane of destiny. Consider the geometric meaning once more. At r equals 2 times g times m divided by c squared, the time component of spacetime is scaled to zero relative to infinity. The light cones, the diagrams that represent all possible directions light can travel, tip inward. At the horizon, one edge of the cone lies exactly along the surface. Inside, both edges tilt toward the center. The universe itself seems to lean. This is why the event horizon is so haunting. It is not dramatic in sensation, yet absolute in consequence. One may cross it without fanfare, but one cannot send news of having done so. The freezing seen by the distant observer and the normal passage of time experienced by the falling observer are not contradictions. They are complementary descriptions arising from curved spacetime. Gravity has done something extraordinary here. It has not only slowed time, it has partitioned reality into regions of no return. And all of this arises from that deceptively simple expression, 1 minus 2 times g times m divided by r times c squared, sitting quietly beneath a square root, determining the fate of clocks, of light, and of causality itself. When one first encounters gravitational time dilation near a black hole, it may seem like an exotic curiosity, a dramatic flourish at the edge of physics, relevant only to distant galaxies and violent cosmic abysses. But nature is rarely so compartmentalized. A principle strong enough to halt time at the brink of a black hole does not politely restrict itself to the extraordinary. It whispers everywhere. The same mathematical structure that governs the slowing of time near a black hole also governs the ticking of clocks above your head. Recall the fundamental expression, time near equals time far, multiplied by the square root of 1 minus 2 times the gravitational constant times the mass divided by the radius times the speed of light squared. In narration, proper time equals distant time times the square root of 1 minus to gm over rc squared. Near a black hole, the factor to gm over rc squared becomes large enough to dominate the expression, but near Earth it is small, very small, yet not zero. Take our planet, insert its mass for m and its radius for r. The fraction 2 times g times Earth's mass divided by Earth's radius times the speed of light squared yields a number on the order of 10 to the minus 9, tiny, yes, but measurable. The square root then differs from 1 by a similarly small amount. Thus a clock at sea level ticks slightly slower than a clock high atop a mountain. Raise a clock by a few kilometers, and it gains nanoseconds per day compared to one below. Now consider satellites used in navigation systems orbiting Earth. Their clocks are higher in the gravitational field, so they tick faster due to gravitational time dilation. But they are also moving rapidly, and special relativity tells us that moving clocks tick slower. The special relativistic factor is given by time moving equals time stationary multiplied by the square root of 1 minus velocity squared divided by the speed of light squared. In narration, moving time equals stationary time times the square root of 1 minus v squared over c squared. Thus, for satellites, two effects compete. Gravity makes their clocks run faster relative to Earth's surface, while motion makes them run slower. When one calculates both contributions carefully, the net effect is that satellite clocks gain about 38 microseconds per day relative to clocks on Earth. Without correcting for this, navigational errors would accumulate at kilometers per day. The abyssal mathematics of black holes quietly ensures that your map application functions correctly. But let us lift our gaze again to the cosmic stage. Near neutron stars, those dense remnants of stellar collapse, the same equation governs the flow of time. Neutron stars possess masses comparable to the Sun, compressed into a radius of roughly 10 kilometers. The factor to gm over rc squared becomes significant, though not yet unity. Time on the surface of such a star runs noticeably slower than time far away. Photons escaping its surface are strongly redshifted. The star's gravity imprints itself upon every signal it emits. Now consider the most extreme case, black holes themselves. When our approach is 2 times g times m divided by c squared, the square root approaches zero. Time relative to infinity slows to a halt. But the implications extend further still. In cosmology, the geometry of spacetime governs not merely the behavior of clocks near isolated masses, but the expansion of the universe itself. My field equations, written compactly as g sub mu nu plus lambda times g sub mu nu equals kappa times t sub mu nu, encode how matter and energy determine curvature. In narration, the Einstein tensor plus the cosmological constant times the metric tensor equals a proportionality constant times the stress energy tensor. These equations describe a universe in which spacetime is dynamic. Time is not a rigid background, it evolves. The rate at which cosmic time flows is linked to the density of matter and energy filling the cosmos. Thus, gravitational time dilation near black holes is not an isolated oddity. It is an intense local manifestation of a universal principle. Mass and energy dictate the geometry of spacetime, and geometry dictates the flow of time. There is a deeper philosophical ripple as well. If time flows differently depending on position and gravitational field, then the concept of a universal now dissolves. There is no single cosmic clock synchronizing all events. The universe is a patchwork of local times, each shaped by its gravitational environment. Near a black hole, this truth becomes dramatic. A distant observer may watch centuries pass while an infalling astronaut experiences mere minutes. Entire civilizations could rise and fall in the external universe while near the horizon, time crawls almost to stillness relative to them. And yet locally, nothing feels distorted. Every observer experiences their own proper time as natural. This is the profound lesson. Reality is relational. Time is not an absolute river flowing independently of matter. It is a participant in the cosmic dance. It bends where mass accumulates. It stretches where motion demands. It responds to geometry with quiet obedience, from the ticking of satellites to the red glow of neutron stars. From the functioning of navigation systems to the fate of collapsing suns, gravitational time dilation weaves its influence. What began as a square root in an equation becomes a principle reshaping our understanding of existence itself. The abyss near a black hole is not separate from your daily life. It is the same law written in bolder ink.